In this video, I'm going to be showing you the elimination method for solving systems of linear equations. And so, basically, we've already discussed the graphing method and the substitution method. And one of the things we've learned is that normally when we solve a system of equations, we get a ordered pair as an answer or a solution. Graphically, when we were graphing these systems, what that means is normally we would graph the two lines, since they're linear equations, and they would intersect at a single point, and that point of intersection was the solution. So that's our most common case. But we also saw that sometimes you could graph the two lines and they could be parallel, which means the two lines have no solution in common or no intersection in common. And so in that case, there was no solution to the system. And then finally, there was the case where we would graph the two lines and they both ended up being the same line. So what do they have in common? They had the whole line in common, and there's infinitely many points on those lines, and so we had infinitely many solutions. We also talked about consistent versus inconsistent and dependent versus independent, and I'll kind of reinforce those concepts as I do this video. So let's go ahead and get started. So first of all, I want to just kind of show you where the elimination method's coming from. And by the way, we also call this the addition method, and you'll see why in just a minute. So let's see, if we had this equation here, 2x minus 3 equals 7, and how about the equation 3 equals 3, what if I were to add the left sides of these two equations and the right sides of these two equations? I would get on the left 2x, now the minus 3 and the plus 3 are 0. On the other side we would get 10. So 2x equals 10, which means x is 5. So do you feel like I pulled a fast one on you? I mean, does this feel like this ought to be legal in algebra? Well, think about it. If you look at what I did here, I really just added 3 to both sides of the equation. And we can certainly add the same number to both sides of an equation. And so for that reason here, since the two sides are equal, we're just adding the same thing to both sides of the equation on top. And so this is the approach that we'll be using, and this is indeed legal in algebra. So let's go ahead and look at number 1. So we're going to add the two sides. On the left side, we'll add our x terms. We get 3x. Notice the y terms add up to 0, y and a minus y. So they basically cancel each other out. And on the other side, you have 6, and so x is going to be 2. So again, most of the time we're expecting to get an ordered pair as an answer. And in fact, we just found the x value of our ordered pair. So to find y, we can use either of our two equations that we started with. I'm going to go ahead and use the first one. It's probably the easiest of the two. So x plus y is equal to 9, and we know x is 2. And so you can see that y would be 7. And so 2, 7 is our solution. Because we have at least one solution, we say the system is consistent. And the dependent versus independent, that basically came down to the situation where they were the same line. That was our dependent case. And so we're going to be independent here. This is not that special case. All right, so this is the most common type of answer we're going to have, where we're consistent and independent, and we're getting a single point or ordered pair as a solution. I would encourage you to try number 2 and then watch the video. All right, so let's go ahead and add the left sides. The x terms are going to cancel each other out, and we're going to have 1y and 8y is 9y, 27 on the other side. So you can see y is going to be 3. And so far we've found the y value of an ordered pair. So I'm going to go ahead and use the first equation, and I'm going to plug in 3 for y. So we'll subtract 3 on both sides, and you can see that x is 4. And so 4, 3 is our solution. Again, we're consistent. and independent. All right, so I want to point something out here. Remember above I had said that we sometimes called this the addition method. There's two things important here. One, we are adding the equations together. We're adding the left sides and we're adding the right sides. But the other important fact, and that comes in the elimination part, is notice in example 1, we eliminated y when we added the equations together. And on number 2, we eliminated x. And so in order for this to work, you're only going to eliminate x or y if they're opposites. And so before you could add them together, you've got to make sure you have either opposites for x or for y. So let's go ahead and look at the next example. We have 3x plus y equals 7 and x plus 2y equals 4. Now you can see, I'm going to go ahead and do this. I wouldn't write anything down. I would get 4x plus 3y is equal to 11. Which is perfectly true, and it's legal to do that. We just did the same thing we've been doing. But it's not really helping us because we didn't eliminate x or y. So let me get rid of what I just wrote there. So what I need to do is somehow create opposites. And what I'm seeing is where this x is here, it would be nice to have a negative 3x there. Now I can't just multiply by negative 3, just times that term. But I can multiply the whole equation by negative 3, and so that's what we're going to do. So I'm going to rewrite the first equation, and I'm going to multiply the second equation by negative 3. So we'll get negative 3x, 2y times the negative 3 is negative 6y, and 4 times negative 3 is negative 12. Now, really what we're doing is we're basically multiplying each side by negative 3. And when we do that, we have to distribute on the left here. And so I don't normally write it this way. If you wanted to, because basically what happens is each term ends up getting multiplied by negative 3. So for some people, they like to do this. It just helps them to remember they've got to multiply every term on both sides by whatever number they're using. All right, but anyway, let's go ahead and finish what we're doing. We'll add the equations together, and you can see x is eliminated. We're going to get negative 5y equals negative 5 when we add. And so you can see that y is 1. And so we know our ordered pair has a y value of 1. Let's go ahead and use, it really doesn't matter, but I kind of like the second equation. Let's plug in 1 for y. That's x plus 2 equals 4, which means x is 2. And so our solution is 2, 1, and we are consistent and independent. All right, I do want to point something out here. Actually, let me erase this here. It's kind of in the way. All right, so I want you to notice that this is not the only way we could have done this problem. If you look at the y's, notice if I multiplied the first equation by negative 2, then I would have a negative 2y in the first equation, and when I added them together, I could eliminate y. So either of these approaches would work quite well. And so, you know, when you make a decision about how you're going to solve one of these systems, you're looking for the easiest way, and there may be more than one good way to solve an equation. All right, let's look at number 4, and I'd like you to go ahead and maybe see what you can do and then watch the video. All right, so first of all, I'm looking at this 3, and I can't really multiply anything times 3 to get negative 5x, so that's not going to help. But look at the y's. I'm thinking if I could change that 2y to an 8y, then that would work. And so I just need to multiply that whole equation by 4. So let's go ahead and do that. Oh, I forgot something. I knew there was something I was missing. Let's go back to number 3 real quick. I just wanted to point out that you can check your answers, and that's true for any of these systems of equations. And notice how easy it is to do. So I'm going to plug in 2, 1 into the first equation. You get 3 times 2 plus 1 equals 7. So that's 6 plus 1, that certainly equals 7. And in the second equation, it's going to be, let's see, 2 plus 2 times 1 equals 4. And you can see that's 2 plus 2 equals 4, and that's true. Now, the math is not always as easy as that, but you could certainly use a calculator to check these quite quickly if the numbers aren't so nice. So let's go back to what we were doing on number 4. So we decided to multiply the second equation by 4. So we're going to rewrite the first equation and multiply the second one by 4. So 4 times 5x is 20x. And 4 times the 2y will give us 8y. Whoops. And then 4 times negative 12 is negative 48. You always want to make sure you don't forget about that constant on the other side. That's got to be multiplied by 4 as well. Every term on both sides. So let's go ahead and add our equations together. We're going to get 23x is equal to negative 46, and so x is going to be negative 2. So let's go ahead and use the, let's see, so we'll use the second equation here. It really doesn't matter. I just thought I'd like the second one a little bit better. I'm plugging negative 2 in for x. We're going to get negative 10 plus 2y is equal to negative 12. We'll want to add 10 to both sides. We get 2y equals negative 2, which means y is negative 1. So again, we're going to be, our system is consistent and also independent. All right. So in all of these cases so far, if we were to actually graph these lines, they would intersect at the points that we're getting here as solutions. All right. Let's move on to number 5. Now, go ahead and look at number 5, and I think you'll see that there's something a little bit different about this one. Notice if I want a minus 5x here, that's going to be kind of hard to get because there's no nice number times 2 that gives me negative 5x. And similarly, I can't really get 10y here by multiplying 3 by some nice number anyway. We'd have to use a fraction. And so in this situation, we're not going to get away with just multiplying one of the equations by something. We're going to have to multiply them both by something. So what I normally do is I'll look at the coefficients in front of x, or you could do this with y too. 2 times 5 is 10. And so what I want to use is I want to get a 10x and a minus 10x for my first terms when I rewrite these equations. So I want to multiply the first equation by 5, and I'll get 10, well, let's see, so we get 10x plus 15y equals negative 80. And then I want to multiply the second equation. See, I need a negative 10x right here. And so I'm going to have to multiply by negative 2. And so we're going to get negative 10x, which is what we were expecting and how we set it up, plus 20y is equal to negative 60. So we're going to go ahead and add everything together. You can see we're going to get 35y is equal to negative 140. And if you divide both sides by 35, you get y is negative 4. So I think I'm going to go ahead and use the first equation. So I've got an ordered pair so far with a y value negative 4. Let's plug that negative 4 into the first equation. We'll get 2x minus 12 is equal to negative 16. Let's go ahead and add 12 to both sides. And then we'll need to, 2 times negative 2 would be negative 4. And so our solution is the point negative 2, negative 4. Again, this is a consistent system and also independent. All right, let's move on to number 6. Now, if you look at numbers, actually, I would encourage you to try number 6, but I'll warn you, this is going to be one of our special cases. So go ahead and try it and then watch the video. All right, so hopefully you're multiplying the second equation by negative 2, so you'll have a 4x and a minus 4x. So I'm rewriting the first equation, and I'm multiplying the second one by negative 2, we'll get negative 4x plus 6y is equal to negative 14. So something interesting happens here. Both x and y are eliminated. We get 0 on the left, and when you add there, you get negative 9. So 0 equals negative 9. That's interesting. That's a false statement. And when we're solving equations and we get a false statement, that tells us there is no solution. So if you think about that, to our three cases when we were graphing systems to solve, this is the case where the two lines are parallel. They have no common point of intersection. That's why there is no solution. And since we don't have at least one solution, this is an inconsistent system. Now, this is not the case where they're the same line, and so we're still independent. All right, let's move on to our last example. So first of all, I look at this, and since we're using the elimination method, I'm going to want to subtract 2x on both sides on the bottom equation. And so we'll get this system here. And now I'm looking at the bottom, and I'm thinking I'd really like this minus 2x to be a positive 6x. So I'm going to need to multiply that second equation by negative 3. So our first equation is negative 6x plus 3y equals negative 3. And in the second equation, we're multiplying by negative 3, so we can get the 6x in the beginning. So we're going to be able to eliminate x. Now, y times negative 3, that's minus 3y. And negative 1 times negative 3, that's going to be 3. So notice this time when we add the equations, everything falls out or is eliminated. So we get 0 equals 0. Interesting. Now this happened when we did the substitution method, so hopefully you remember. But basically what happened here is when we added the equations together, everything fell out. Well, why did that happen? Well, it's because they're the same equation. They're equivalent, even though they look a little different. You can see that this equation here can be, if you just multiply the first equation by 3, you get the same thing. So these are equivalent equations. They have the same solution. And so that's why everything fell out. So our solution is infinitely many solutions. So basically, we said these two lines, when you graph them, they're the same. So what do they have in common? The whole line, and every point on the line represents a solution. So there's infinitely many of them. We're consistent since we have at least one solution. And then finally, this is the case that we call the dependent case, which kind of makes sense since they're essentially the same line. And so this is a dependent system. This is the only one that's been dependent. Now, if you're in a beginning or intermediate algebra class, that's probably as much as you need to know on this problem. This is actually a college algebra course that I'm teaching right now, or I'm making it for college algebra students. And there's a better way to write our solutions. We said there's infinitely many solutions, but that's really kind of lame because I haven't even told you one of them. And so here's what we can do. In fact, we already have an equation solved for y. We have y equals 2x minus 1. So we can actually write our ordered pairs in the following form. The first value we're going to write as x, and then y, we have a way of writing y in terms of x. So y is 2x minus 1. So that's the relationship between x and the y value. So this, in general, is how we can write all the points that are solutions to this system. Basically all the points that are on either of these lines, since they represent the same line. So for example, if I let x be 0, 2 times 0 minus 1 would be negative 1, would be the corresponding y value. Or if I let x be 1, then the corresponding y value would be 2 times 1 minus 1, which is 1. And so those are just some of the many, infinitely many solutions. Our final answer, though, here is this point, x comma 2x minus 1. All right, and that is the end of this video.